Hello everyone, in this series of videos we'll talk about how to solve questions in Physics C, AP Physics C Mechanics test for 2023. And you'll see that in this video we will not just talk about the solution, but also the background knowledge that is being tested in the exam. So there are three free response questions. So this video is about the first one. This question is about spring and ramp. All right, so now let's look at the question first, and then we'll talk about how to solve it. A block sitting on a horizontal surface is pushed against a spring. This spring is called spring P that is attached to a wall, compressing the spring a distance x, shown in the picture. So here's the origin of the coordinate system. That's x equals 0 position. So now right now the block compressing the spring to the right side, a distance x. The block is then released from rest. Now once it is released, the spring force will push it to the left side. And once the block passes the origin here, the spring will just stop. And they will separate. The block and spring will separate. The block will keep moving to the left side. However, the spring will restore its original length and stop here, right here at the origin. Okay, so now the block slides along the horizontal surface and up a ramp, reaching a maximum height h max p. Frictional force between the block and all surfaces are negligible. So we can declare all the friction forces. Now, a student usually set up to compare the h max p for spring P with the maximum height h max pq achieved with a different spring, spring Q. Each spring exerts a force of magnitude F on the block that varies as a function of the distance x that the spring is compressed, as shown in this figure, figure 2. So we do have a solid line curve for spring P, and for spring Q is the dashed line curve. Okay, and the horizontal axis is the position, the compression x, and the vertical axis is the spring force generated by such a compression. Now for spring P, we know this curve is represented by kx, which is a straight line going through the origin, and the slope is k. Okay, and we also call that k spring constant, and it has value 100 newtons per meter. Now for spring Q, a similar expression is given by c times x to the power 1/2. So that's what we call a nonlinear spring. So the relation here is not the linear relation we saw earlier. It's a nonlinear one. And it could happen that in the future, they might test you like another kind of nonlinear relation, such as maybe 3/2, etc., or x squared, etc. Now here, the coefficient of c is also given. It's 20 newtons per square meter. Square root meter. Now let's look at question A. For the experiment, the block is pushed against one of the springs, compressing the spring a distance x equals 0.01 meters. The block is then released from rest. In trial 1, spring P is used, and in trial 2, spring Q is used. So we have the diagram for two trials. On the following dots representing the block in the experiment. Draw and label the forces that are exerted on the block at the instant the block is released. So that is essentially the free body diagram problem. So we need to figure out what forces are acting on the block and then draw them according to their relative strengths. So that's the requirement here. Each force must be represented by a distinct arrow starting on and pointing away from the dot. Okay. Now, the length of the horizontal vector should represent the relative magnitude of the horizontal force, and the lengths of the vertical vectors represent the relative magnitude of the vertical forces. Okay, so that means that when I draw these two diagrams for the two situations, I need to compare the two horizontal spring forces, and I should draw their length, right, according to their relative strengths, which we can calculate. Okay, so because we're given this x value. Okay, so now let's first calculate the two spring forces, right, using the expression given. So first we calculate the spring force Fp, which is Kx. So now K is 100. X is 0.01 Newton per meter. So we get 1 Newton. Now force Fq from spring Q will be Cx to the power 1/2. C is 20. 0.01 to the power 1/2. Okay, so now you see the question designer, they actually use these, give you this really nice number, 0.01, so that you can take this square root very easily. It's simply just 0.1. So you get 2 Newton. So that means that Fq is twice Fp. Okay, and when I draw the free body diagram, I should consider that relation. Okay, so now for trial 1, here's the dot representing the block. Now when I draw the spring force Fp, let me draw some arbitrary lengths horizontally to the left. That's Fp. Okay. Now if I do trial 2, here is the dot again representing the block. Now I need to draw twice the length of this Fp. Okay, so here is about the same length as the original Fp. Now I need to double that, so I need to continue like this, and that's Fq. Okay, that's spring force Fq. All right, so that's about the horizontal, because there's no friction force, so the spring force is the only force acting on a block in the horizontal direction. Now about the vertical direction, because gravity is acting, of course, it's acting on the block, right? So it's no vertical downward direction. So we draw that, and let's do this. It's gravity. We call it mg, and also the same thing here. It's mg, and they should be equal, right? Because it's the same block. Now in the vertical direction, there's also the normal force, right? The ground, the surface here is supporting the block, right? So in the direction of the normal force should be upward, balancing the gravity. So I should draw a normal force which has same length as mg. So these two have same length, these two arrows. That's also a normal force, okay? Same length with mg. Okay, so that's all we have for the free body diagram for question A. Okay, so that's for question A. And we do have 2 steps. So that's question A. Step 1 is figuring out the 2 force, and step 2 is drawing the diagram. Now question B, sub question 1, what features of the graph in figure 2 could be used to estimate the work done on the block by each spring as each spring is compressed? So let's look at the figure 2 first. So we do have this force versus the compression x, okay, or the displacement x of the block. Okay, so we'll talk about that. And before we talk about the feature of the diagram, let's think about what is the work done on the block. And here's the diagram. So we have a spring force acting on the block, and here is the coordinate system. So we're going to use the origin, same origin as in the original diagram. And the coordinate system is to the right. X is to the right. Okay, so now the spring force is pushing right on the block to the left. And we also have like normal force and gravity in a vertical direction. Okay, however, the block will have displacement along this direction. Okay, so that's the you can say the displacement delta S. Force, I also want to change it to a vector notation. Okay, so the work done by the spring force, let's say, is F dot delta S. Okay, so at delta S here, I'm right now assuming is some small finite displacement, okay, along that direction. Now we see these two vectors are in the same direction, so the work here should be positive. So the spring should do positive work to push the block to the left side, increasing its kinetic energy. Now think about the work done by normal force and work done by the gravity. Okay, so these two forces are in 90-degree angle. Okay, so the gravity and normal force, they perpendicular to delta S, so the work done here should be 0. There's no work done by these two forces. Okay, just something I want to talk about before I do calculation on the work done by the spring force. Okay, however, the force here is a variable. It's not a constant force. It depends on the displacement, so we need to do integral instead. Okay, so the work done by spring on the block is force the infinitesimal displacement ds, and the integral here, in order to do that calculation, I want to represent the both vectors here in terms of the unit vector. So let me draw that unit vector. Usually we use I hat to represent the unit vector along the positive x-axis. But of course, the like different textbooks, they use different notations. Some textbooks use x hat, etc., and there might be other notations. But anyway, we're using this unit vector I hat, okay, to represent this direction. I would say that is like a reference direction. So now F in terms of I hat would be negative kx I hat. Okay, the negative sign is because the force is to the left side, which is negative. Okay, negative direction. And ds here, the displacement can be written as dx times I hat. All right, so now let's figure out the lower and upper bounds of the integral. The block here is being pushed from this initial position, let's say x here, okay, to the origin. So the integration lower bound should be x, upper bound should be 0. All right, so I hat equals 1. Okay, so that's something we know before. And now the integral here becomes a scalar integral. So we have negative kx dx, x goes from x to 0. Now in order to differentiate between this x and that x, so I'm going to change this one to x prime, right, because it's an integral, it's a variable in the integral. This x here is the is some finite value, a definite value that we know. Okay, so now with that notation, we got negative 1/2 k x prime squared. So now x prime goes from x to 0. So we do have 1/2 k x squared. So I assume that this result is very familiar to you. In the textbook, we did this kx relation, a linear spring system, and then we calculate that work done by those kind of springs. Okay, so that's spring P. Okay, so now let's do spring Q. I'm going to write it here so that we can save some space. Spring Q. Okay, so the work done by spring Q will be same thing here, but now the expression will be different. It's negative c x to the power 1/2, and I'm going to change it to x prime, and then dx prime. Okay, so x prime goes from x to 0. So now that integral, let's see, is negative. So I'm going to add 1 here, so that's 3/2, so that's 2/3 c x prime to the power 3/2. X prime goes from x to 0. That integral will be 2/3 c x to the power 3/2. Okay, so that is the work done by spring Q. Of course, in the actual exam, you don't want to do all these things, right? You just want to answer this question. So now what I'm trying to say is that this integral, right, represents the work done by the two springs, and in the diagram, it equals the area under the curve. Okay, so if you look back at the at figure 2, then there will be area under this solid line that represents the work done by spring P, and the dashed line here under the dashed line will be Q, work done by Q. Okay, so the answer here is the area. Yeah, area. Now, the second question, there's one compression distance x naught for which the maximum length, maximum height h max reached by the block is the same, regardless of which spring P or spring Q is used. Predict whether the value of x naught is greater than, less than, or equal to 0.04 meters. Use the graph in figure to justify your answer. So let's look back at the picture again. So that's a really special point, x equals 0.04, this point. So now if I think about the area under the two curves from x equals 0 up to this point, right, 0.04, I can clearly see that the area of the spring Q is larger than the area under the curve for spring P. Okay, so let's write this down. So the second question of part B is, so at x equals 0.04, the area of P is less than the area of Q. Okay, and also that is true for all the x positions less than 0.04, right? Less than 0.04. So so the answer cannot be less than 0.04. It can only be greater than 0.04, and by simply just looking at the picture, I'm guessing somewhere here. Okay, somewhere here, so that the area under the solid line is the same as the dashed line here. Okay, and that's a way of calculating that point exactly. Okay, but anyway, the answer here is greater than. Okay, the exact answer can be given by these two integrals here. Okay, so let's see if we can figure that out. So the exact point. So the answers would be here would be s would be greater than 0.04. Exact point of x naught. So we should write down the two works. WP equals WQ, and WP is 1/2 kx. Suppose it's x naught, so that will be x naught squared equals 2/3 c x naught to the power 3/2. Okay, and then that equation will give us the x naught solution. Okay, so I'm gonna skip that point, and later on we'll find some value from the picture, approximately the value of x naught, when we were given more conditions there. Okay. So question C, on the axis provided for both spring P and spring Q, sketch a graph of the maximum height H max reached by the block as a function of the distance each spring is compressed for values of x ranging from 0 to 0.1 meters. Clearly label the curve for spring P and spring Q. Yeah, sorry, I forgot to mention that why we're doing that, the comparison of the work here, because it's due to the work and kinetic energy theorem, which says that the total work done on the block, and in our case, this total work here is simply just the work by the spring, is equal to delta K, okay, the change of the kinetic energy of the block. And the change of the kinetic energy of the block is referring to, so here is the initial kinetic energy of the block, which is at rest. Okay, so that will be 0. And the final position, the final kinetic energy of the block would be the block's kinetic energy at x equals 0. So right at this position here. Okay, so let's write this down. So it's K final minus K initial, and it's simply just K final, right? Because K initial is 0. It's at rest. And that's not it, because not all of it, because we need to consider the block climbing up the incline. So with this initial kinetic energy, now the final kinetic energy becomes initial kinetic energy. So the block will climb up the ramp. So that's x equals 0. So at that instant, it has this V final or K final. It will climb up the incline, and all the surfaces are smooth, so the kinetic energy will be converted totally into the potential energy of the block. So you need to calculate like the height here, H max. Okay, so the energy conservation says that mg H max equals K final, and it's the same K final we wrote down earlier, and then that's why it's the work done by the spring. So for spring P, it will be WP equals H max P mg H max Q will be WQ. Okay, and in order for these two height to be the same, that defines the x naught, right? According to the question, then we need to have these two equal. Yeah, sorry, I forgot to say that before I talk about the WP equals WQ, right? That come from here. Okay, so now for the third question, we need to plot the height H max as a function of the compression x. Okay, and we actually already have the answer. So that is according to these two equations. Okay, so now we know WP is 1/2 kx squared. WQ is 2/3 cx to the power 3/2. Okay, so we can calculate H max for spring P would be kx squared over 2mg. Okay, now H max for Q would be 2cx 3/2 divided by 3mg. Okay, since we're not given the value of mass m, so when you plot the diagram, right, we can simply just say, how about mg here equals 1, then we simply just plot 1/2 kx squared in the diagram, and then this one is 2c x to the power 3/2 divided by 3. And these two curves are given by, this one is easy, right, quadratic. So since k is 100, right, let's plug in k, so we get 50 x squared. So it's going to be just a quadratic curve going through the origin, and then for this one, it's harder to draw, but one thing you can do is that you can plug in this given value. Let's say x equals 0 here, x equals 0.02, 0.04, etc. You just figure out these several points and then draw those dots first, and then you connect them. Okay, so now let's see. So c is 20, so we have 40 over 3 x to the power 3/2. Okay, so you can write out a series of points. For example, let's say x equals 0, then HP, HQ, HP will be 0, HQ is also 0, right? And then x equals 0.02. Let me try this one. So 0.02, I will get the, let me do some calculation here. So get 0.02, also 0.02. Now for this HQ, so we have to the power to the cube, and then take square root times 40 divided by 3. So it's 0.0338. Let's try one more, 0.04. So it's 0.08 here. Okay, so it's 0.107. Okay, so now let's say 0.06. .18. 0.196. Okay, so you can see up to 0.06, the H max Q is still greater than H max P. However, they're getting closer now, right? Closer now. And let's try one more. Let's say 0.08. I want to see the transition from. So that's 0.32. I want to see the transition from HP less than HQ to HP greater than HQ, and let's find the transition first, okay? And now let's calculate 0.08 for HQ. Yeah, now we see the transition, so it's 0.302. Okay, so now you see the HP now is greater than H max Q. Okay, so when we draw the picture, let me do it right here. Let me draw a small picture. That's H max, and that's X. Okay, so at 0 they're the same. Okay, so I'm gonna use the black dot for HP. Okay, so that's black dot. So we have 0.02, 04, 06, 08. Actually, one more, it would be 0.1. So now I have 0.02. That's for HQ. 0.08. Okay. And then, okay. So if I do this in scale, then it will be, I will not have enough space. Okay, so let me change a little bit. Let's say, draw some schematic relations. Okay, something like that is increasing. Quadratically. If I connect all of them, right? So I've get, I will get the curve for spring P. Okay. Now for the red point, for the H max Q, I'm going to use the red dots. Okay. So they start at the same origin here. Now that is higher than x equals 0.02. Is higher than H max P, almost double the height, and then there you get even, let's see, it's 0.02 difference, still 0.02 difference, but it's not the double, right? So it's somewhere here, and then 0.06, they're getting closer. Okay, now 0.08, I mean, you'll be smaller than the HP. Okay, and I assume they will continue to trend even smaller than HP for x equals 0.1. Okay, so we'll get a curve. Yeah, sorry, they should be continuous. I don't think I can draw that, but it'll be something like that. Okay, and I have to say that the curve here is not accurate. It should be something like going like this. Okay, not from curve down to curve up. It's always like curving up along that direction. Okay. All right. So that is the drawing of the two diagrams. Oops. Okay. All right, let's look at question C. Spring Q is attached to the wall and is at equilibrium. So that's spring Q. Now block A has a mass of 0.12 kilograms. So that's block A sliding down. And block B has mass 0.07 kilogram. Block A is held at rest at the top of the ramp, and block B is at rest on a horizontal surface. The student releases block A and it moves down the ramp and collides with block B. The change in vertical height of block A is h equals 0.75 meters. After the collision, the blocks stick together and move to the right, compressing the spring. Neglect all the frictions. Sub-question 1. Calculate the velocity of the two block system immediately after the collision between blocks A and B. Okay, so here's question C, part 1. Okay, now when the block A slides down, the total mechanical energy of A is conserved. So right before the collision, we call this one initial position of A and that's the final position of A. So the mechanical energy initial position equals the final mechanical energy of the block A. And we should use the bottom level as the zero potential energy level. Okay, so at the beginning, because it's at rest, so the only mechanical energy component is the potential energy, so it's mg capital H. Okay, so capital H is the number given in the question. Now that equals the final mechanical energy of block A, and at the final position its potential energy becomes 0. So it only has the kinetic energy of the for A. Let's call that V naught. Okay, so I'm going to say that is the velocity before the collision, so that's why I call it V naught. Now from here I can calculate V naught equals square root 2gh. That's step 1. Now step 2, block A collides with block B. Okay, now before the collision, A has velocity V naught that we just calculated right here. However, B is at rest. And we know the collision will conserve the total momentum of the system, right? So if you think about the system here as A and B together, then the momentum before the collision equals the total system's total momentum after the collision. Okay, now this momentum should be thought of as the summation of the two momentum, PA plus PB. Okay, so now here is before the collision, and because only A has momentum, so we say MA VA here. Okay, also for the previous M, I should say MA here just to avoid confusion, although they cancel out. Alright, that's the total momentum before the collision, and I should also change this one to V naught because that's our notation earlier. So that equals the momentum after the collision. After the collision, they stick together and move together with a common velocity. Let me call that VC. So that is MA plus MB times VC. That's the common momentum, okay, common velocity VC. And from there, I can calculate the velocity after the collision for the two blocks. Okay, so it's given by MA V naught over MA plus MB equals MA square root 2GH over So that equals. So MA from the question is 0.120. G is 9.8. H is 0.75. Okay, now MB, so MA, let's copy that. MB is 0.07. Okay, so the calculation will give us, let me check the answer here. .42 meters per second. Okay, so you can also check this calculation, and if you find any other, let me know. Okay, now the second part of the question is calculate the maximum compression of the spring. So that refers to the process when the two blocks moving together, like this instant is like the initial instant we see, and then it will compress the spring. Okay, and at the maximum compression, they will stop, and all the energy will be converted into the potential energy of the spring. Okay, and let me tell you that for spring Q here, okay, so the potential energy expression will be 2/3 Cx to the power 3/2. So that comes from the integral that we did earlier. Yeah, right here. We did that integral earlier. In fact, we did that before that. It's this expression, right? So I will explain why we have that later on. But right now, let's use this result first. So we say the potential energy represented by, for the spring Q is represented by this expression. Okay, so we should convert all the energy, the kinetic energy that we have earlier, into this potential energy. So we can write down 1/2 MA plus MB VC squared equals 2/3 Cx 3/2. Okay, then we can calculate the x value equals. So you need to collect all the terms, like move 3 to the left side, 2 to the downstairs, and then divided by C, right? So we have 3/4 C here, and then MA plus MB times VC squared, and then we need to do the 2/3 here, okay, to calculate the value of x. And then you can plug in all the values. 3 MA again is 0.12, 0.07, that's for MB. VC is 2.42 squared, and then divided by 4 times C. C is 20 to the power 2/3. And this number turns out to be 0.12 meters. Okay, so that's part C. Okay, so now let me explain why this potential energy is such an expression for spring Q. Okay, so the definition of the, so this one is like some background knowledge. So if you don't want to listen to this, you already know, you can skip this part. Okay, so definition of the potential energy, okay, is defined as following. So first, you want to calculate the work done by a force F. F should be conservative force. F is conservative force. Now that work equals negative delta U. Okay, and delta U is defined as U final minus U initial. Okay, so you want to do calculation for the work done by a conservative force using the definition F dot ds, and then you want to go from the initial to a final position. Okay, so in our case here, I want to go from initial xi to a final x final, and then force here, let's say for spring Q, would be cx to the power 1/2, and then dot ds. Now we need to take care of that sign, and then dx there. So that's the same as what we did earlier. It's just that I changed the integration bounds from xi to x final. Goes from xi to x final, so that will be different from earlier. Okay, so that will give us negative 2/3 c to the power 3/2 x goes from xi to x final, and that is, let me continue here, c x final minus x initial. Okay, and if I compare this expression to negative U final minus U initial, then I can conclude that U final is 2/3 c x to this power 3/2. X initial is this xi initial to the power 3/2. And remember, we picked some arbitrary points, xi as final, right? So that would mean in general, U is a function of x given by 2/3 c x to the power 3/2. So for nning, that's for nning x. Okay, so that's why that's the expression for potential energy for spring Q. Now for spring P, you can do the same thing, but I assume you already know that from the textbook. So U for spring. So spring P will be the linear relation. Spring will be 1/2 kx squared. Okay. All right, let's do the last part of the question. Spring Q, where Fq equals c times 3/2, c times x to the power 1/2, is replaced by a different non-linear spring, spring R, and the procedure described in part C is repeated. So spring R, Fr equals d, now it's a different coefficient, d times x to the power 1/2. The maximum compression of spring R is greater than the maximum compression of spring Q, which of following correctly compares the constant C and D. Now remember, we already have that expression for the compression X, right, given by this expression here. Okay, and the initial kinetic energy of the two blocks are the same for both springs. So we would say for question D, we will say for spring Q, the maximum potential energy is 2/3 c to the power of x 3/2 max x max for Q. Okay, so that will be equal to spring R, which should have the similar expression. Now is max R. Okay, and they should be equal. That's an important thing. They should be equal. And then we already know that the spring R has a greater compression. So X max P is less than X max R. Sorry, not P, Q. X max Q, right? This one is less than max R. So that would mean the coefficient C need to be greater than D. So the answer is this one, C greater than D. Okay, all right, so that's all for the question number 1 of 2023 AP Physics free response. Thank you for watching.